Hi everyone, welcome to this lab on sequential optimization techniques. So the files we are going to use are all named with dff underscore const. So these are the files we will be using. The TBs are of course the associated test benches. So let's look one by one what is happening here. So let's take the first circuit dff underscore const 1.v. As I said, dff, the switch for opening multiple files in GVM is -o, so I'm using that. So what happens in this code? So if you see dff const 1, so we are talking about dff const 1. What happens in this code? If you look at this code, we have a flop because always at pos edge clock comma pos edge reset, this infers a flop. So we have a flop. So reset. So upon reset, the Q is going to get 0 and else Q is going to get 1. That means the D input is tied to 1 tick B1. So is this a sequential constant? We have discussed this during the presentation of the optimization also. Let's draw a waveform and check. And we will simulate this design also to ensure that our understanding is correct. So let's say my reset is applied something like this. The reset is applied something like this. This is my reset. This is my clock. My D is always 1 tick B1. So since reset is applied like this, the Q will be always 0, but removal of reset does not mean that Q is going to be becoming 1 immediately. It is going to wait for the next clock edge. So it has to wait for the next clock edge to become 1. It cannot become immediately. It cannot become, this is your Q. Many people get confused. They think that this code will result an inverter between reset and this one. This is what they expect, but this is not what we are going to get. This is not what we are going to get. We are going to get, the Q is going to become 1 on the next rising edge of the clock. The reset may get deasserted anywhere here. Doesn't matter where it is going to get deasserted, but Q will wait for the clock to become 1. So it's not a simple inverter. Since the event of Q becoming 1 is sort of synchronized to the clock or is associated with the clock, the flop will be inferred in this design. Okay. Whereas let us look at dff underscore const 2. We will simulate this also and check. We will synthesize, simulate, do everything and check here to see our understanding is correct. Okay. So here I have a flop which is getting a set. This is my Q, this is my D, this is my clock. Now if there is a reset, so this reset is actually working like a set. So this is a reset pin, but upon reset, the reset is actually a set here. It's going to make the Q2 go 1. And D is also tied to 1. That means, let's draw the clock here. Now, this is my reset here, similar way. This is my reset. Now, because of reset here, the flop is going to be 1. And you are removing the reset, so it continues to be in 1. And on the edge of the clock, it continues to be in 1 because D is tied to 1. So everywhere the Q pin is going to be 1. It's constant. Correct? So let us simulate this before we synthesize it and check what is going to happen. So as we have shown, the associated name with TB as prefix will be the associated test bench. So dff const 1, TB underscore dff const 1 is the associated test bench. Okay. So let me generate the test bench. So the tool is iverilog dff underscore const 1 tb underscore dff underscore const 1 dot v. Okay, so it's going to generate a executable file dot slash a dot out. So if you see, it's going to jump the VCD. So let's open the VCD in GTK wave. So this is my clock, this is my reset, and this is my Q. I'm going to put 100%. So see here, this is beauty. So kindly observe here. Here, let me zoom in here. See, this is exactly what I was saying. Reset went low somewhere in between, whereas Q is waiting for the next rising edge. It's not going one here. It's not going one here. It's waiting for the edge of the clock. Since it has to wait for the edge of the clock, you cannot do it without the flop in picture. So this circuit will infer a flop. In the contrary, if you see the other circuit, let me open the, let me sort of load this design in the simulator. We'll see the output of both the waves side by side. So this is so here also we have a clock, reset, and Q. Sort of going to put this 100%. Now you see here, whether there's a reset, whether there's a set, doesn't matter. Q is always 1. In contrary here, if you see, I have to wait for the clock for Q to become 1. Q is otherwise 0. If you see, otherwise Q is 0. It has to wait for the clock. So because it's sort of, the waveforms are sort of looking very packed here, it's looking like immediately it's going 1. But when you zoom the real detail, you will be able to see only when you zoom it. When you zoom it, you're clearly seeing that the Q is waiting for the clock edge. Okay, this is what our simulation is telling. So let's see what happens when we synthesize it. So Yosis is the tool. So let's launch Yosis. First thing, we will read the Verilog file. So read liberty, the library, read liberty -lib, mylib, libsky. Now read Verilog, dff underscore cons 1.v. Now synth -top const 1. Now here we need to do one step extra, because so far in the design we have been seeing only combinational circuit, but here since there's a DFF, we need to do something called as DFF libmap. DFF libmap, again we have to point the same. This is for mapping the DFF, because sometimes libraries may so be written in such a way that for sequential circuits you are having separate libraries, and for combinational circuits you are having separate libraries. So DFF libmap is going to tell you, or you may have in certain cases special flops. So DFF libmap is the switch which is telling the synthesizer for sequential circuits, mainly for DFF and latches, what library it has to pick. So it's the same library for us. So we will read the same library. I'm sorry, we will use DFF libmap. Yeah. This command is DFF libmap -liberty. Okay. And now we are going to do abc -liberty /mylib lib. Okay, and we will do a show. See, exactly this is what we are seeing here. See, this is our DFF const 1. See, this is a DFF. This is a flip-flop, correct? So this is a flip-flop which is having a clock, D pin, reset pin, and a Q pin. D is connected. This is what we expected, correct? So D is connected to 1, and I have a reset and I have a Q. Now this standard cell library is expecting a reset to be active low. but we have coded a active high reset in our design. So the tool is inferring a inverter here in the reset path, because the library cell is expecting a active low reset. It is invert, and our code is, look at the code here. Our code is saying if reset. For sake of argument, if I have written if not reset, it would have not inserted this inverter, because by default the library is having a active low reset. So because we coded it as active high reset, it is inferring a another inverter here. So this is like bar of a bar which becomes reset. So reset is getting connected here. This is what we expected. Okay. So now let's try the same thing with read verilog dff underscore const2. What is happening here?